Okay. Everyone is admitted. I will start now the Facebook Live. Okay, we're live on Facebook. Okay, so just a second. Okay. So we're starting now. Hello, everyone. I'm Victor Bar, the Israeli Regional Manager of Asteroid Day. And I want to welcome you all to an Asteroid Day event, Asteroids vs Planetary Devices, with Dr. Aviram Weiss and Michael Shwartz. Today, it's the 15th of February. Exactly 9 years ago, a meteor exploded over the Russian city of Chelyabinsk, and the world was forced to face a new reality that there is no place on Earth safe from asteroid impacts. And our main concern today are not the dinosaur killers, but rather the small ones that can destroy a city or a region. The main purpose of Asteroid Day is to raise the public awareness of asteroids, both as a threat to Earth's cities and population, and also as an exploration and scientific opportunity. And we at Asteroid Day Israel want to reach the Israeli and the Hebrew-speaking public for the same reason. Today, both our talks will focus on space missions that are not directly connected to asteroids, but you will see that everything is connected and asteroids can be researched everywhere. Our speakers today are space enthusiasts and professionals, and I'm sure you will enjoy hearing them passionately talk about their field of interest. You can ask them questions by writing them in the chat, and I will ask our speakers to answer them during the Q&A sessions. But before introducing our first speaker, I want to thank my partner and friend, Itai Leon, our gifted space graphics professional, for handling all the graphics of this event. I hope you all saw the video he made. If not, go directly to Facebook, to Asteroid Day Israel page, and have a look. Also, I want to thank Saulo Machado of Asteroid Day Global for helping me organize this event by providing the Zoom account. And as always, great thanks, besides Saulo, to Colleen, Stuart, and Danica Remy for all the great work they're doing on Asteroid Day. And now, let us welcome our first speaker, Dr. Aviram Weiss, a volunteer in the educational team of Space IL. These people are great. They go day by day, school by school, and teach kids about space, the moon, and of course, the Beresheet mission that has placed Israel in the honorable club of countries that reach the moon. So today, Aviram will talk about Beresheet 1 journey from a meeting in a pub to a not that soft landing on the moon, and will also reveal some of the plans of Space IL for the next mission. Aviram, the Zoom is yours.
Thanks, Victor, for this presentation. Let me share my screen, and hopefully we'll be able to see everything normally. Okay, so actually I'm not going to talk about spacecrafts and asteroids and engineering. I want to focus more about dreaming, because I think that's what's common to all great innovations and findings in science in the last maybe 10 millennia. So Beresheet's mission is also a dream. It has begun as a dream of actually 3 young engineers, Yariv, Kfir, and Yonatan. They met first digitally on Facebook, but then in real life in a pub in Holon, and started imagining how to send a spacecraft to the moon as part of the Google Lunar X Prize competition that put the challenge of private groups to send a private spacecraft to the moon for the first time ever, actually. We see the three dreamers actually in that pub in a reenactment image, and you can see the pages they brought with them and started planning the spacecraft on that meeting. And actually these are the images of what they thought this spacecraft would look like. And let us focus on the first image or design of the spacecraft. Actually, it looked like that. As simple as that, it has all the ingredients that are required to go to the moon. The spacecraft has a body with a fuel tank inside, a main engine, and some landing pedicles or legs. This is pretty much everything that is needed to go to the moon. Its size initially on their dreams and plans was a little bit more than 1 liter. So it would be very small. And they started actually designing this landing on a rocket that would send this directly to the moon is impossible because we don't have any such rockets anymore. The last ones that were available were used in the early 70s to launch Apollo missions to the moon. And since then, that was Saturn V. Since then, 5 decades have passed, and we don't have these very large and very powerful rockets anymore. So we have to rely on a regular rocket, such that would send our spacecraft to an orbit around Earth. And so the spacecraft would be left around Earth and then have to navigate its own all the way to the moon. So it cannot be that small, 1 liter by size. It has to be much larger. So they redesigned it, and by 2012, that was the design of the spacecraft. Then not named yet, but this size is already about 1 meter high and about 1.5 meter wide, with its legs spread wide open. But then again, it was not efficient enough, so they redesigned, and on 2014, that was the design, much taller and narrower. And then when they started testing this design, they discovered that it's not stable enough. So when it lands on the moon, there's a big chance to fall over on its side, and that's not what we wanted. So they redesigned, and you can understand that this spacecraft is exactly how when you want to go from dream to reality, that this was the final design of the spacecraft. Now it already got, and on this design, wide when the legs are open. Of course, this is a design drawn by designers, actual professional designers, and not by engineers. When the engineers built this design, it looked a little bit different, maybe less aesthetic. That's the real thing that was actually built. So this is Beresheet #1. This is the actual spacecraft that went to the moon. We can see the 4 fuel tanks that compose about 80% of the spacecraft's weight when leaving Earth. The main engine is here in the middle. We can see the 4 pairs of minor engines that navigate the spacecraft through. In most places in the world, we launch things to space towards the east, and Israel is limited because of geopolitical issues. So launches from Israel are usually done to the west, which limits the weight and velocity that we can gain during the launch. So we contracted with SpaceX for a launch on a Falcon 9 rocket. Just for the proportion, if we said that Beresheet is about 1.5 meters tall, then this rocket is 72 meters tall. If you want to see the proportion, these are lightning posts. So this is a real tall building, 20-something stories high. And it is composed actually of three main components. There's the engines here. There are 9 engines, hence Falcon 9. And then there's the cargo bay here on top. And all this tube here in the middle is actually the fuel tank. So if we open up the cargo bay on the rocket and look inside, then this is what we see inside. This is the envelope of the bay. And all this big thing here is actually not Beresheet. This is an Indonesian satellite. And on top of it, like a crown, we see the golden Beresheet. So since we usually pay by weight, you can understand that Beresheet was practically hitchhiking its way to space. So this is a very small spacecraft in a very low budget project, done quite fast in space. From dream to launch, it took about 9 years. That's very, very fast in terms of space projects. And it aims to an almost impossible mission to go all the way to the moon and softly land on it. So once this is all ready and the spacecraft, the missile is already ready for launch, actually we all went to the States, to Miami, and witnessed that launch. And this is what 2 of our founders, Kfir and Jonathan, had to say during that very exciting day.
It's a big moment. We are really excited. We're sure that you are also. So one thing we always do in every event is we take a selfie. 3, 2, 1, to the moon!
And actually, yeah, we did go to the moon, and it was a very nice and warm February evening in Miami, in Florida, and we were all out in the open, just in front of that rocket. We were about 4 kilometers away from that, and maybe as opposed to what everyone imagines about launches, though we weren't in a control room, no screens and countdown, etc. Just out there on the grass between us and the rocket. There's 4 kilometers of water, and it was about time for launch. It was 7:45 evening, and all of a sudden we see smoke going out down from the rocket, and then fire ignites, and the rocket starts climbing in the sky, and it was silent. We didn't hear anything, no noise, no engine rumble, just silent. And we see that rocket started climbing out in the sky, and about 15 seconds later, we hear and feel the wave of noise from the rocket coming towards us. And we watch the rocket disappear in the sky and look at each other and then ask, what now? Well, the engineers were very anxious because there were about 30 minutes of black, of nothing. We didn't hear anything from Beresheet. We didn't know if it is a good spacecraft that functions in space and would go all the way to the moon, or we launched a dead iron ball worth $100 million to space. So it took about 30 minutes until Beresheet leaves the rocket. And then when it goes to space, it starts sending back information, telemetry, and then some images and videos. This is actually the first video that we received from Beresheet once it's separated from the rocket. And you can see the rocket here, and this is the thruster. And now you can see the leg spreading over. So this is actually the first action that Beresheet does after leaving the rocket, actually because these legs are the only moving parts inside Beresheet, and you want to get rid of movements as soon as possible, because this is a very sensitive point in any spacecraft that you cannot control. So that went okay. And then we started receiving images, and they were very surprising, even though they were exactly what was planned in advance. This is the first image that arrived, and it revealed this very exciting sign that was on Beresheet. It says "Small country, big dreams," and in Israel, in Hebrew, Am Yisrael Chai. That's an ancient saying about the Jewish nation, the nation of Israel. And then a few hours later, we got another image looking like that, and seeing all these images, rumors started to spread that this is fake, this is Photoshop. You can even see the strings here that are attached to the Earth across the green screen. While being there, I can assure you that this is not a fake image. But one question that raised was, if that is taken, if this image is taken in space in complete darkness, where are all the stars in the sky? You don't see anything. No moon, no stars, no asteroids, nothing. So thinking about it, you would expect a very bright sky full of a lot of stars if you're in the darkness of space. But actually, if any of you ever had the chance to play with cameras, you know that if you want this part, the lower part of the image, to be in focus, and you want this sign to be in light, you have to lose focus on all these small elements that are in the background. So this is actually the reason why you don't see any stars in the background of these images. But we went further, and it was okay until we started having some problems. But just to show you the difference between direct launch towards the moon, what was initially planned in 2010, and the actual route that was then chosen and fulfilled. So if that's Earth, then the rocket would leave Beresheet in a very narrow route or orbit around Earth. The farthest point from Earth was about 70,000 kilometers, and the nearest point was about 200 kilometers. That's very, very close. And then every time we went to the nearest point, to Perigea, Beresheet had to turn on its engine and give some more thrust, and then widen the orbit further and further and further, until finally reaching about 400,000 kilometers from Earth. That's a little bit more than the distance to the moon. Then going all the way back to Earth, completing another circle, and on the last orbit, or the last turn around, we actually had to catch the moon. That's a maneuver that was had to be done very, very accurately in the exact time and speed and length to actually break Beresheet from its orbit, very fast orbit around Earth, to be caught by moon's gravitation, and then change its orbit to orbit around the moon. And that was a very, very anxious point, or very sensitive point in the journey. But finally it was done, and I must say almost perfectly performed as planned. And so we found ourselves orbiting now the moon, in actually the first time ever that a private spacecraft is reaching the moon, the first time ever that an Israeli spacecraft is reaching the moon. Yeah, thanks, Michael. It was the smallest object that was sent to the moon. It was the cheapest object that was sent to the moon. So many, many achievements. But then again, our mission is not to go to orbit around the moon. Our mission was to land softly on the moon. So this is the next step of the journey. And in the meanwhile, we can try to enjoy some images that Beresheet sent from the orbit around the moon. This one is taken from about 340 kilometers height from the moon's surface. And this is even closer. You can see the lit area or the lit side of the moon and the dark side at that point of the moon. And actually also in this picture, you can see this small round white object. That's actually you. This is Earth as it appeared on Beresheet's camera around the moon. And so the next step would be, as I said, to softly land on the moon. Actually, the mission was to convert this fake image. This is a simulation image that was prepared during the preparations to launch. And it was planned to be taken during landing. And the mission was to turn this into that. And this is an image taken during landing. And you can see we are very, very close to the moon's surface. And that's the actual image taken during landing. But as probably most of you already know, this fairy tale didn't really end very well. So I apologize for the Hebrew sync, but this is the original imagery or footage from the control room in Yahud during the landing. We'll first see and hear, and then I'll try to explain in English what we saw.
לפי כל הסימונים, לצערי הרב, אנחנו כנראה בינתיים לא נהיה מדינה רביעית בעולם, אבל אנחנו בכל מקרה הגענו להישג אדיר. היינו מאוד קרובים לירח, ואנחנו על הירח. אנחנו גם על הירח, אבל לא כנראה בצורה כמו שרצינו, ואנחנו נבדוק עוד פעם וננסה להבין מה קרה.
Okay, so what we see here is the actual control room of Beresheet in Yahud during the landing. We heard the voice of Alex Friedman, the head of the, actually head of mission during the flight, just a few seconds after he discovers that Beresheet didn't land softly, but quite fast crash on the surface of the moon. And then next to him sits Yoav Lanzman, the chief engineer of Beresheet, and he tells him, well, Alex apologizes that we're probably not the fourth country that has arrived to the moon. And then Yoav corrects him that we actually did arrive to the moon, but maybe not as softly as planned. So we are on the moon, but then again, not a complete success. So it may be a very nice debate whether Beresheet 1 mission was a success or a failure, and I think a little bit of both. But let's try to understand what went wrong in the journey. So actually the problems started way back a lot before the crash on the moon. The first problem was that we discovered the star tracker, that navigation component was dazzled by the sun. The star tracker is actually a camera that takes images of this dark sky and looks for stars and compares those images to a star map that's in its memory. And in that way, you can understand the direction of Beresheet in space, in 3 dimensions, of course. You cannot tell the speed or location, but you can tell quite exactly the direction that Beresheet heads. This probably happened because of small particles, dust-like particles that were part of the getting out of the rocket of Beresheet, and they sat on the camera of that star tracker and caused sunlight to enter the lens. And actually, it was discovered quite early in the journey and really caused a lot of problem, because if you don't know at which direction you point, there's no point in turning on the engine, because then you don't know where you're going to. And to overcome this problem, the engineers of Beresheet had to think very hard, and then they came in 24 hours, they came with a bright solution. If this star tracker that points to a certain direction is dazzled by the sun, let's flip the whole spacecraft on to the other side, take an image and understand our direction, and then flip it back to its position. So this way they could do this maneuver every once and again, and understand the exact direction or the exact pointing of Beresheet. So this was a very big problem that was overcome by some creativity, but it had cost, because in order to do so, you have to create a new software, a new set of commands that you send to Beresheet, and train Beresheet to do something new that it actually wasn't built for. And on top of that, we had another problem, and that may be something that we deal with in other places. And I told you that in every orbit, every time we came to the closest place to Earth, Beresheet had to turn on its engine and give some thrust so that we widened the orbit. And actually, just before turning on the engine, we discovered that the computer had reset itself. So it would turn off exactly when we want it to be on, to turn on the engines. And the reason for that was that unplannedly, Beresheet entered Van Allen belt. That's an area around Earth that includes a lot of magnetic fields and radiation and particles that interfere with the normal work of a computer. So in order to protect itself, the computer would shut itself down and then restarts after a while. But that wouldn't allow the engine to turn on. So again, another few circles around Earth were spent, and the engineers sent a new set of commands to Beresheet, so that it now holds the procedure not to turn off the computer in very specific times, so that it can turn on the engine. Again, this is something that interfered with the basic software and the operating system of that computer. So every time the computer had to reset itself, it would not only have to reload the operating system, but also had to reload all these order sets that were sent throughout the journey. So this is a procedure that takes a lot of time, and we'll see in a moment that that was actually crucial during landing. So when we arrived to landing, after all this successful journey, during landing, the IMU, the inertial measurement unit of Beresheet, that was supposed to tell the exact inertia and speed and three-dimensional vector of the spacecraft, started sending garbage, some error mistakes to the computer. And in order to prevent this from happening, then actually Beresheet had a procedure to shut this IMU down and go to a redundant IMU, a spare IMU that we had, IMU number 2. But it would have done so if not for lack of some emergency protocols in our control room, which caused some of our teams to send a command to Beresheet to reset the computer and prevent the mistakes from IMU. So that would have gone quite well, but remember that the previous mistakes or the previous problems caused a restart to take about 30 seconds instead of 3 seconds. So 30-second restart time during landing, that's a very, very long time. And actually, that's what prevented Beresheet from completing the soft landing that it planned. So as we know, Beresheet did not successfully land on the moon, but we are actually good Israelis, and good Israelis leave mark wherever they go. It doesn't matter if it's New York subway or Eiffel Tower in Paris or the moon, and we are Israelis, so we had to leave a mark. This is actually an image of the landing site of Beresheet, taken by the LRO, the Lunar Reconnaissance Orbiter, NASA spacecraft that orbits the moon constantly and takes its image. And that's an image of the landing site taken in December 2016. That's way before Beresheet's journey. And if we look at another image of the same LRO, the same place, after Beresheet's landing, this is how it looks like. So let me go back. This is before and after. So we're good Israelis. We left a mark. Beresheet was here. But setting that aside, actually, that's something that we had to rethink about. So we did all this amazing journey. We built a spacecraft. We went 6 million kilometers in our orbiting way to the moon. We captured the moon, or we were captured by the moon's gravity, and we almost landed on the moon. Now, there's another problem, that during all this time, all these years of planning and building, and of course, during the journey itself, we did something else. And maybe that's the real reason why I am here and why we're doing this event, maybe by the angle of Space IL. Aside of building a spacecraft and sending it to the moon, we wanted to create an educational effect in Israel. We wanted to make youngsters in Israel enthusiastic about space, about engineering, about going back to the moon, and about fulfilling their dreams. So parallel to the engineering process, we did an educational process, and a team of dozens of volunteers, some of them I see here in the crowd, constantly talk to students of all ages, maybe ages 3 to 93 or something like that. And we meet them constantly and tell them about the journey of Beresheet and that very big dream. By the time Beresheet was launched, we already managed to meet about 1 million students in Israel personally, face to face. That's pretty much all of them. And so promising all these youngsters that we can go to the moon and we can fulfill our dream and land on the moon ends with a big crash. So now when we overcome this mourning of crashing this project on the moon, we have to rethink what we're doing. And actually thinking about all those 1 million students and even more now, we had practically no choice but to restart the project and do a regenesis, go back to the moon. So it was a long process of more than a year of rethinking what to do. Is it worth to do another project all from the beginning, just for these 2 minutes that we left in that Beresheet's journey? And finally, this is the answer. Oh, sorry for that. Beresheet 2 project is already on its way. The main issue is very clear in several points. One, we're going back to the moon. We plan to land softly and successfully this time on the moon. Beresheet 2 spacecraft is going to be majorly based on Beresheet 1. There are many components of the spacecraft that are reused by design. Of course, not material because that's on the moon, but the design is reused. But Beresheet 2 is going to be more complex than Beresheet number 1. So it's going to be actually 3 spacecraft that are joined together. One main spacecraft, the mother spacecraft, is going to get to the moon and then orbit around it and not attempt landing. And once a successful orbit is achieved, 2 minor spacecraft are going to be released from the main one, and each in a different point of time and a different point in space is going to land on the moon in 2 different locations, one on the near side of the moon and the other one on the far side of the moon. And then we'll have communication between the mother spacecraft and the 2 landers, and also between the mother spacecraft and Earth. And aside of sending them to the moon and landing them on the face of the moon, we plan to do several educational and research activities with those spacecraft. We're planning several projects with students from here in Israel and from other places in the world, so that they can communicate with the 3 parts of Beresheet and do short-term projects with the landers that are going to be landing and survive several days on the surface of the moon, but also long-term projects with the mother spacecraft that is going to be with the orbiter that is going to be orbiting for several years around the moon. So this is also an opportunity for long-term research and educational projects with Beresheet. So I hope that was a short glimpse of what the journey looked like in Beresheet 1 and a little bit of what we're planning for Beresheet 2. I can say that we are already on the way. There is almost a complete plan of the new spacecraft. The budget is already almost entirely available, and the plans currently are to launch Beresheet 2 around the end of 2024. So that's really around the corner in terms of space projects. That would be all for today, and I really hope you enjoyed. If there are any questions or remarks, I'd love to have them.
And a great talk, Aviram. Very, very interesting. Can you please tell us about the scientific equipment that was on Beresheet 1 and what is planned to be on Beresheet 2?
Okay, a very interesting question. Actually, on Beresheet 1, we had 2 pieces of scientific equipment. One was planned in advance, very long time before launch, and that was a magnetometer that was planned to measure the magnetic field of some rocks on the moon. We know from previous missions, from NASA and Russian and Chinese missions, that different rocks on the surface of the moon are magnetically charged. We don't know why, we don't know how much and at which type or distance around the moon. So we plan to measure that very short-term magnetic field of several rocks. We did manage to do some measurements during the orbit and during the landing. Of course, we didn't complete this experiment because we didn't have a successful landing, but there are some findings that are quite interesting in that research already from the partial data that we have. And the second part, or the second piece of equipment that we had, was the NASA equipment, actually a reflector. NASA planned to use Beresheet as a spotlight on the moon, send laser beams to the spacecraft, and get it reflected back to Earth so that we can more accurately measure the location and the distance and the movement of that spacecraft on the moon, and actually of the moon itself. That unfortunately was not successful because after the crash, we didn't have the chance to allocate that reflector. So that was not completed. As for Beresheet 2, I cannot say yet what type of scientific equipment we're going to have because it wasn't determined. But we know that a certain amount of weight and space on the spacecraft, both on the orbiter and the landers, are dedicated for scientific equipment, and it will be determined in the next year or two, and then we'll have some, I hope, very interesting experiments with Beresheet 2.
Okay, thank you very much, Aviram. And now for our next speaker. He is truly unique even among the space enthusiasts community. He was the first to make an automated telescope and find the first intergalactic supernova in 1997. He discovered 12 comets, yes, 12 comets, it is not a mistake, with his handmade telescope, got a grant from NASA to his Tanagra Observatory to observe asteroids and follow up on NEOs. He knew Carl Sagan and many other famous scientists, and is one of the voters for the Planetary Society grants up to $20K, and most importantly, he is making Aliyah in a few months. Let us welcome Michael Shwartz to talk about Hubble and Webb space telescopes, infrared astronomy, and much, much more. Michael, the Zoom is yours.
Thank you very much, Dr. Weiss. It was very interesting. Excuse me very much. Believe it or not, I have never seen a rocket launch.
Okay.
So Victor, it's up to you. Start showing the PowerPoint.
Yeah, you want me to show the PowerPoint or you're showing it? Okay, I will show it, no problem. Just a second. Okay, I will now share my screen. Okay. Just a second. Can you see my screen?
Not yet, but in a moment. Now we do.
There we go.
Perfect.
Okay,
Michael,
thank
you
you.
can continue.
Excuse me. First of all, I am dressed because I am in the Wild West, and this is what I do when it goes out. Everyone thinks Arizona is one hot desert. It gets very cold here. So on the left, you see a drone picture of my telescope to go into the nearby town and do public outreach. There is nothing like showing a child the moon. It is wonderful. Next slide, please. James Webb is a very interesting man because most of the time telescopes are named after astronomers or the people who give the money. In his case, this is not true. Next slide, please. I'll go through a short biography, but the basic point here is he was in the US Space Agency from 1961 to 68. He did more for science than anyone else in NASA, and certainly deserves having this miraculous telescope named after him. He was also had conversations with President Kennedy. He was very much celebrated here. Next slide, please. Victor, next slide, please.
Yeah, sure.
Okay, Edwin Powell Hubble, 1889 to 1953. He was obviously an incredible astronomer, established the Hubble constant, and his Atlas of Galaxies was quite famous. I even used it for my early 1997 hunts for supernova because there were no digital sky survey disks available. Notice that I put in red, excuse me, Henrietta Swan Leavitt. Behind astronomy are many, many, many women who are never given credit. And I believe in this. Women should be invited into engineering, astronomy, mathematics, all the technical fields. So I think this is very important. And of course, Hubble's main contribution was to show that the universe is expanding. This was earth-shattering because at the time, many theorists believed in the steady state theory, in which case the universe was not expanding. So this is a tremendous accomplishment. Next slide, please. There's a picture of Edwin himself at work. We can go to the next one, Victor. That is the Auschen-Schmidt telescope. Notice he is smoking around the telescope. That is no longer allowed. This telescope is still in use. And my friend Mike Brown is using it to look for trans-Neptunian objects. So old telescopes never die, only astronomers do. Next slide, please. This is the famous Hooker telescope. Now, I have visited this telescope before it was refurbished, and it was amazing. It was all direct current. There were relays clacking, making noise. And at the console, there were just two switches, slew this, slew east, slew west, well, four, north and south. They had eyepieces for looking at the setting circles. It is the most amazing telescope. I wandered around. I found spectrographs lying on the floor. I found logbooks with Humason, Shapley, and Hubble, and their entries in these logbooks. But I do not steal, although I was very tempted. But incredible. Next slide, please. Okay, a short history of infrared astronomy. It began in the 1830s with William Herschel. You'll see later, I visited the South African Large Telescope and also his first observatory in the Southern Hemisphere. Notice that water vapor is in red. We will see that is the reason why infrared astronomy does not work very well from ground-based telescopes. Next slide, please. Okay, this is the Spitzer. It is a mini web. This is not the first time the United States has sent up an infrared telescope. And if you notice, it has a sun shield and it looks like a mini web. So this is kind of the explorer that set up the concept for the web. The results were so astounding that they had to make a larger telescope to investigate even more. Next slide, please, Victor. Okay, there's a lot of telescopes here, but the ones I have listed are the ones I visited. Keck in Hawaii, Hooker in California, the South African Large Telescope, and that's where I saw Herschel's old equipment as well. The Large Binocular Telescope you can see on a mountain right outside my home. And of course, I was at Palomar and saw the Auschen-Schmidt. But you can see here, we have some very large telescopes planned, huge ground-based telescopes. There's a lot of work to be done in optical astronomy yet as well. Next slide, please. This is just to show that John D. Hooker was a businessman. He gave the money. Oh, I forgot to mention one thing, and you will see it in the next slide. That mirror is made from French wine bottles. The earlier mirrors, of course, were speculum, and they had to be constantly resilvered. At that time, Corning Glass in New York, which produced the big eye, the Palomar telescope, could not produce glass. When I looked under it, it is so full of bubbles. And a lot of those bubbles actually reached the surface. But that's the best they could do at the time. A little bit about John J. Hooker, rich man, of course. His ancestors were involved in the Constitution of the United States, who was appointed President George Washington. So John J. Hooker goes way back. Next, oh, by the way, the gentleman taking the photograph there is part of the refurbishing of the Hooker telescope. If you ever come to Mount Wilson, you can actually pay and use it. It's a small sum, like $90 US a night. It would be an amazing experience. Of course, they now have a CCD camera on it, and you can replicate the work of great astronomers before. Next slide, please. Okay, again, Spitzer, Mini Webb. We've already discussed that, so we can move on. This is an image of M81 taken by Spitzer, and it's a teaser. We're beginning to see what the universe looks like in infrared. And again, this was the incentive for Webb. Next slide, please. Okay, here's the problem with ground-based telescopes. You notice that oxygen and water block infrared light. That is why we have to go into space. There is no alternative for an infrared telescope than being in space. Next, please, Victor. This is a little simple diagram showing the blockage by the atmosphere. I have visited the Arecibo telescope in Puerto Rico when it was in operation, but unfortunately there was a terrible accident and I don't think it will ever be rebuilt. But the Chinese are building a much larger one and hopefully they will share data with the world. Next slide, please. Lagrangian points. I won't talk about Lagrange, but he was a master of Newtonian physics. And he determined that there were these stable points where, for an example, if you know about the Trojan asteroids around Jupiter, they are at Jupiter's Lagrangian points. So this discovery showed us that we can put a telescope and have it relatively stationary. Next slide, please. This is Webb's orbit. And once every 68 days, it's relatively straightforward, except for, and it's at the L2 point of the Lagrangian point. And we will talk about the halo around. I mean, why is Webb going around the Lagrangian point rather than just sitting there? We will talk about that later. Next slide, please. Now, NEOWISE, which was created by the incredible Amy Mainzer, It will also sit at L2. And when it comes to NEO discoveries, she is the absolute queen and master of this. She started out with an earlier project called WISE that was an Earth orbiter, but of course it had to be cooled. So it had liquid hydrogen tanks. And sooner or later, those liquid hydrogen tanks have no more liquid hydrogen. So WISE is still orbiting the Earth, but is no longer operational, or is in minimal operation right now. A huge number of near-Earth objects were discovered by this. And that's why NASA funded her to go ahead and create NEOWISE. Next, please. That's Amy. She actually did a Star Trek: The Next Generation. The right one shows that she was an advisor for the movie Don't Look Up, which is on Netflix. And anyone within the sound of my voice who has not seen this should see this movie. There's Leo DiCaprio, who was in the movie. And I might add that since I'm on Instagram, Leo DiCaprio is the leading movie star who supports environmentalism on the Earth. He's a very strong voice and an Oscar-winning actor. You have to admire this man. Oh, by the way, that is not Amy. You can see, I can't see it because it's hidden, but it's another woman who was in the movie. Next, please. Okay, as I said before, NEOWISE will go to the L1 Lagrangian point. That's an artist's concept of what it will look like. Of course, it has solar panels, and you'll see underneath it also has a heat shield. And again, it will have a halo orbit, and we'll talk about that later. Next, Victor. Webb is the Christmas launch. And this is the final liftoff. And while I can't see it, there is the length of the trip. Next, please, Victor. This is the top of Webb. That's the sun shield behind. You can see the secondary mirror. And those are segmented mirrors. When I went to visit the Keck telescope, I got to look at what they call actuators. These are tiny real-time devices that actually bend the mirror to get rid of all star twinkle. And Webb will have the same kind of actuators. It took a long time to develop electronics that were fast enough to take a star that literally dances due to atmospheric distortion and make it look like it is standing still. Absolutely necessary in any kind of astronomy. Next, please. That's the bottom of Webb showing the sun shield. Obviously, it must be kept cooled. The Webb does not have liquid hydrogen tanks, or it may have some backups. I haven't investigated that. If I was designing it, I would have some backups in case something went wrong. But obviously it must be shielded and kept very, very cold. Next, please. This is the Webb color filters. It is a monster. I'm going to, if you bear with me, go to my hard copy of this. The Hubble telescope has 3 filters: red, green, and blue. In typical amateur imaging, they have what's called LRGB. Red, green, blue. The L stands for luminance filter, which lets as much light in. My own telescope, known as Big Blue, had ultraviolet, blue, visual, red, and infrared. That's a remarkable instrument, and we will talk about that later. Next, please. Webb research projects. Obviously, black holes, search for dark matter and energy, calibrating the Hubble constant, which is constantly happening, planetary and galaxy imaging. But the most interesting to me is exoplanets. And we'll see why in the next slide. We have the Perseverance rover. We may find fossilized organisms. The Chinese are doing the same. And most surprisingly, the United Arab Emirates has an orbiter, but they're investigating the Mars atmosphere and not looking for life. Next, please, Victor. This is the IR spectrum of chlorophyll. Chlorophyll, for the uninitiated, is what makes plants move, what makes plants live. The Webb telescope will be able to identify a chlorophyll signature in exoplanets. This means we can actually find an exoplanet and prove that there is plant-based life, if it exists at all. Next, please. Oh, there's liftoff. Sorry about that. Got in there. Okay, this is the sequence of what happens to Webb when it took off. First of all, it was unshielded. The tower was extended. The secondary mirror was extended. The primary for 29 days. It takes a 1.51 kilometer trip to the L2 halo orbit. For 6 months, it prepares for full-time science operation. This lets everything cool down, calibrating the mirrors, instruments, etc. Its expected life is 5 years, 10 years, hopefully, if there's enough fuel to maintain the halo orbit. Obviously, to do this, it has to have thrusters. And there are standard thrusters that are used on every planetary probe in order to keep it moving. Next, please, Victor. A little bit of American Webb madness. You can buy pendants, you can buy earrings, you can buy t-shirts. There are people making Webb-shaped cakes. America is very excited about Webb, but the entire world should be, because what it delivers will be amazing. But America gets a little kitschy about these things, but that's America. Next, please. NEOs. Depending on what you're looking for, a near-Earth object can be a PHO, which is a potentially hazardous object. There's 27,000 known. 11 are short period. And the most important thing is at the bottom, and that's why it's in red. Well, let's talk about what's above in red. 65 million years ago, the Earth was impacted by probably a very large meteor, possibly a comet. This caused the extinction of the dinosaurs, which are why we are here. 65 million years ago, there were mammals, but we all look like rats. And in an odd way, we can thank this asteroid or comet, because dinosaurs will still be roaming the Earth and we would still be like little rats. I should add the dinosaurs are still roaming the Earth. Birds have been reclassified as Dinosauria. So every time you see a bird, say, hello, dinosaur. Oh, the DART mission. This is set to launch November. It has been launched. And in October 2022, the USA will make its first attempt to try to move an asteroid out of the way, because we expect another big hit. It will come. Will it be another 65 million years? It certainly won't be tomorrow. It certainly won't be in our lifetimes. So any children watching out there, it's okay. We have nothing to be afraid of. Next, please. This is the Barringer meteor crater. I have stood right there. Barringer was an interesting character. He bought this land because he believed there was a tremendous amount of iron under there, and he wanted to get to the iron. What he really didn't know was it pretty much vaporized after impact, and you can find what's called tektites. These are a kind of volcanic or heat-generated glass all around it. The Barringer family still owns it. You have to pay tickets to get there. But if you're ever in Arizona, this is a must-see because it's one of the best preserved craters in the world. It's 50,000 years old. Native Americans came here about 12,000 years old, 12,000 years ago. So they didn't get to witness it, but a lot of animals did. Next, please. Okay, 65 million years ago, this is the dinosaur killer. It hit in the Yucatan Peninsula, and I can't pronounce that, but there is a crater, part on land, part underwater. These cenotes are very interesting. These are sinkholes. You go down them, full of water. By the way, I also have a degree in archaeology. So these cenotes are very interesting to me because the Mayan Indians used to make sacrifices. And when divers go down there, they find incredible jewels and complete skeletons, etc. Of course, there's the famous T-Rex. Everyone knows Tyrannosaurus Rex, the great meat eater. Next, please. Okay, this is my friend, Leonid Edwin. I actually met him in Moscow, and we've been in competition for years to see who can get more NEOs and who can get more comets. Leonid, if you're watching, sorry about that. But myself, and I have to mention my partner, Paolo Holderson, he is responsible for a lot of Tanagra observatories. He's an amazing man, has a PhD in general relativity, a master's in meteorology, and he loves NEOs, and he's still selling his multi-user system. So he's active and working. Next slide, please. Okay, this is Tanagra observatories, not today, but as it existed. That's my house. I'm sitting there right now. We will get to the telescopes that were there in the next slide. And there is my email down there. If anyone has any questions beyond the question and answer period, I would be happy to take email questions and answer them as best as I can. Next slide, Victor. Okay, this is the brightest comet we ever found. This is obviously 247P Tombaugh Tanagra. When Clyde Tombaugh was looking for Pluto up in Flagstaff in the north of the state, he found a comet and lost it. But Paolo and I managed to recover it Therefore, we got credit for it. Nearby is an amazing man named David Levy, who has dedicated his life to comet hunting, and he is the lead biographer of Clyde Tombaugh. So when I got this picture, I drove up and I gave it to him. He was very, very happy to get it. Next slide, please. Tanagra Observatories started in 1995 when I was 45. And you can see the plaque that my friend and we built it together, dedicated to the greatest show in the universe itself. In the center, excuse me, I've done a lot of asteroid naming. Unfortunately, the Minor Planet Center, because of COVID and staffing problems, is no longer naming asteroids. But I honored my mother with this, and as she came close to death, she would hold it very close to her. And if you read it, it essentially says, she taught me classical music, which I love. I hope to get to the Israeli Symphony, by the way. Of course, at 71, I also like classic rock and roll. But one of the commandments is honor thy father and thy mother. And I follow this one. On the right is the only award given for a discovery of a comet. As you can see, it's called the Edgar O. Wilson Award. This man died, left some money, and I got about $3,000 US for every comet. I should mention that in the past, an Italian astronomer, Donati's comet, the prizes were much bigger. The Italian government gave him his own home and made him tax-free for life. I wish that still existed. Next slide, please. Okay, this is how it looks right now. Due to a certain Italian astronomer who I will not name, an outreach astronomer, I was forced to sell the telescopes. And you see what it is right now. I am very proud. Our home is carbon neutral. Those are solar panels. That's where my wife and I and our dogs sit out at night, look at the stars. The room I'm in is actually the Airbnb. For a while before COVID, we had an Airbnb. And I would go out in the back with my green lasers, and I have Canon image stabilized binoculars, and I give tours of the cosmos. It's a lot of fun. Everyone asks the same questions. Why do stars have Arabic names, for instance? Where are the star growth centers? This is wintertime, so of course I show them Orion, the largest and best star growth system. And unfortunately, the winter Milky Way is looking out of our galaxy, as Shapley proved. And the summer Milky Way here is still amazing. And a quick plug. A plug in America means an advertisement. My wife and I are looking for a long-term rental for this place. So anyone within the reach of my voice, get in touch with me through my email. Thank you and shalom. I'm ready for questions. Thank you, Dr. Weiss.
Okay, thank you very much, Michael. Let's see about the questions. First of all, I have a question. Can you please tell us a little bit how it's like to work with NASA on rediscovering NEOs and determining their orbit, how it's like?
Well, first of all, I should mention that the telescopes began in 2000. And at that point, I essentially invented internet astronomy. So it was a business. Tanagra Observatories Ltd. is an American corporation, was an American corporation. So I sold time to universities all over the world. It was the first of its kind. My friend Paolo developed a multi-user system that would take many users and optimize the chance for every object they looked at to be at the zenith. One of the users, Michael Shara, determined the nova rate in M32. Now, I got tired of this, and I thought, why not get a NASA grant? It is a very, very, very difficult process. Universities, they have entire grant writing departments, but I had to write this grant myself. And the specifics come down to exactly what font you use. And there are pages and pages and pages of instructions. But I got the grant. It was in excess of $500,000 US. And for 3 years, we discovered many NEOs. And then later, with unfortunately a telescope that I didn't show called Pearl, that was the comet discoverer. I should add, in case my friend Tim Spar, who's also a deciding vote in the Planetary Society, is not watching, that I refused a second NASA grant to do the same thing. And NASA was so upset, they sent him out to talk me out of it. But they wanted me to do exactly the same thing for 3 years. And I had a brilliant plan for expanding it to a third telescope in California that would have incredibly increased our discovery rate. The follow-up was done with Pearl, which was a 0.4 meter f3.75 Newtonian wide field. And we used Monte Carlo simulations, all kinds of things, because catching them on the second opposition is very, very difficult. Following them deeply down to VMAG 22 is easy. But the next time around, who knows? They may have had an encounter with Venus. So we had to do Monte Carlo simulations in order to know where to look.
Okay, thanks. Aviram asks, would you please elaborate on the reason why Webb Space Telescope orbits L2?
Very easy. Obviously, it is always in Earth shadow, but it is not always in moon shadow. So the reason for the halo orbit for both Webb and Neowise is to keep it in Earth and moon shadow.
Okay.
Thank you.
Anand asks, in what ways would amateurs contribute here after in the advent of technology?
This is where the Planetary Society comes in. Any amateur who has a reasonable track record of some research, even shows some promise, can apply for a Planetary Society grant and get up to $20,000 for new cameras, new telescopes, new mounts, anything they need to continue their research. This is a wonderful thing. It is the only grant, and not only that, NASA required that I could only hire Americans. The Planetary Society awards can go to anyone in the world. One of the ones I recommended was one in South America, because the Southern Hemisphere is unrepresented by telescopes. We need to see what's there. By the way, when I was in South Africa, I saw the Magellanic Clouds. They do look like clouds. It was amazing. Even though Magellan never made it home, his name is immortal.
Danny asks also about L2. How does one orbit a Mussels point like L2?
Using thrusters. Most thrusters have hydrazine in them, which is simply a fuel that it's like a little rocket, and it can move any spacecraft around. I should add at this point that at my age, I've been very lucky. I saw Sputnik. I saw the entire solar system open up to new horizons. I even had a visit here by some French astronomers who were doing a Pluto occultation before New Horizons.
Wow.
I should also mention that I've seen 12 total solar eclipses as well. And this has made me a world traveler and a travel photographer. So it looks like 12 is my magic number. I don't think I'll see any more.
There's a question that interests me very much. What can you tell us about Carl Sagan?
Here's what happened. My senior year in high school, my father moved us from New Jersey to Missouri, which was a very strange environment for me, a totally different culture. So I buried myself in research. I did what's called a Miller-Urey experiment. This was an early experiment where you could send a spark through ammonia, methane, and water vapor and immediately produce organic compounds. It showed that life wants to happen from inorganic compounds. That's why the galaxy is full of life. Most of it may be green slime, but there's no question life is there. So by winning what was called the Missouri Academy of Sciences Science Fair, I was sent to New York City, where Carl had a symposium on the origin of life. He was an amazing person. He treated me the same as all the other scientists there who were interested in it. I was 16 years old. We had long discussions. We went out to lunch together. And that's what makes him amazing. He took a 16-year-old kid and he treated me as if I was a researcher, which I was. And we talked about the same things. A great man, unfortunately, died too young. He is always in my prayers. And of course, anyone should be able to, if they can find it, I will bring the DVDs for Cosmos, because that was his production. And that was on public broadcasting. By the way, I also met Neil deGrasse Tyson, and he has a lot of competition. American TV has about 300 channels. So he has to cut through a lot of noise. But back when Cosmos came out, there were 6 or 7 television channels. So Carl Sagan was heard loud and clear. In fact, I will show you something. This is a replica of the record that went on Voyager 1. And it contains a brilliantly crafted way of trying to get an alien civilization to find us. Mostly a map of pulsars, but there's a recording that's full of music too, music from all over the earth. And recently I looked at a letter that one of the pieces of music was Chuck Berry, an early rock and roller. And one of the jokes at the time was the aliens would send more Chuck Berry. But Carl and Andrewian, his wife, wrote to Chuck Berry and thanked him.
That's incredible. Okay, are there any other questions? I'm still looking at the chat. So no questions here. Okay, so thank you very much, Michael. I want to thank our speakers for their brilliant talks. I feel that we could stay and listen to them for hours, but our time is up. For those who missed or want to watch once more, the lectures will be available on Facebook on the Asteroid Day Israel page. Thank you for joining us. Goodbye.